Think about the last time you typed a message to someone in an Indian language online. You probably used English letters, right?
Hmm.
It's handy, sure, but you've probably noticed it doesn't quite capture everything that, those unique sounds and, well, the beauty of the actual native scripts.
That's right. While typing Indian languages using Roman letters, it's convenient for quick chats across India's diverse languages, definitely. But it does lose some of the precision
Hmm.
of the original scripts.
Right.
And India has this incredible variety of languages. I mean, different families, most using scripts derived from Brahmi, but also Arabic-derived scripts, and even Roman in some cases.
Okay, let's unpack this then. Today on the Deep Dive, we're looking at a brand new resource. It's called Aksharantar,
Hmm.
and it's designed to tackle exactly this challenge, converting between Roman script and the many Indian language scripts. So if you've ever wondered how we managed to communicate in so many languages online, or you're just curious about the tech behind it all, this one's for you.
Yeah, get ready for that sort of aha moment when you realize just how huge this effort
Yep.
is.
Absolutely.
And what's fascinating is our source today. It's a research paper called Aksharantar, Open Indic Language Transliteration Datasets and Models for the Next Billion Users. It comes from the teams at AI for Bharat and IIT Madras.
That's the Indian Institute of Technology, Madras, a top research university.
Exactly. And they worked with Microsoft on this. They've created something really, really significant, a massive new collection of data, and crucially, the AI models that actually learn from it.
Okay, so our mission for this deep dive is pretty simple then. Understand what exactly Aksharantar is, why it's such a big deal, really, and what possibilities it opens up for Indian language computing. Let's jump in.
Sounds good. The need for something like Aksharantar, it really comes down to how vital transliteration is in the Indian context.
Hmm.
You just have so many languages and their own scripts in everyday use. And while, yeah, many people are comfortable typing on Roman keyboards, I mean, they're everywhere, right?
Yeah.
There's still this strong desire, and often a real need, to communicate and create content in their own native scripts. Using Roman letters is, a useful workaround, but maybe not the ideal long-term solution for everyone.
Exactly. What we really want is for the technology to take that Roman script input, the stuff we type easily, and just smoothly turn it into the correct native script. That's the dream, really, for a lot of users.
Precisely.
And that brings us straight to Aksharantar itself. What exactly is it?
Okay, so at its heart, Aksharantar is a publicly available collection of data, specifically for transliterating between Roman script and various Indian language scripts. But what makes it stand out, really, is its sheer size.
Okay, how big are we talking?
We're talking about a data set with a staggering 26 million pairs of Roman script and native script words.
26 million. Okay, wow. That's way beyond what I was imagining. And how many languages does this cover?
It includes 21 Indian languages. These come from 3 major language families, and they're written in 12 different scripts.
12 script.
Yeah. And to really get a sense of how much of a step forward this is, think about this. Aksharantar is 21 times larger than any similar public data set that existed before.
21 times.
Yeah. Think about it. Previous data sets were maybe like, I don't know, a single shelf of books. Aksharantar is a whole library. This massive increase in data, that's the real game changer here. It lets the AI learn all the subtle rules of transliteration in a way that just wasn't possible before.
Right, it needs that volume.
Exactly. And it's actually the very first publicly available data set for 7 of these languages and for an entire language family too.
Wow. So where did all this data come from? It's not like someone just sat down and typed all 26 million pairs out, right?
No, not entirely. The researchers used a few pretty smart ways to gather all this information. A lot of it was automatically collected or mined from existing online resources, things like Wikidata.
That's that huge online knowledge base.
That's the one. Also, the Samanantar collection of translated texts, and Indicorp, which is a big collection of text in Indian languages. But importantly, they also had human experts manually create some of the data too.
Okay, that makes sense. So the mining gets you the volume, but why did they need to collect data manually on top of all that?
That's a really important point. While automatically collecting data is fantastic for getting a huge amount, it often has its limits.
Like what?
Well, for example, this kind of automatically mined data tends to have a lot of proper nouns, names of people, places, and maybe the words that are just used most often. You see this in older data sets like Dakshina.
Right.
This can mean that some languages, and maybe more importantly, some less common ways of transliterating words, they might not be well represented. So manually collecting data helps fill in those gaps, making sure the data set is more varied and, well, more representative of how language is actually used.
Got it. So they didn't just build this massive training data set and stop there. They also wanted to make sure it was good for testing how well transliteration technology actually works in practice. That's where this Aksharantar test set comes in, I guess.
Exactly. Alongside the main training data, they created the Aksharantar test set. This is a separate collection, about 103,000 pairs of words across 19 of the languages. And its whole purpose is to let researchers really closely analyze how well different transliteration methods are performing.
And what makes this test set so special? It's not just a random bunch of words, is it?
No, not at all. It's very carefully chosen to include a really wide variety of words. This includes words that originally come from the Indian languages themselves, native origin words. Yeah. Also, words borrowed from other languages. Common everyday words they call this subset AK freak.
Okay, AK freak for frequent.
Right, and then words chosen specifically to represent a wide range of letter combinations, or n-grams. That one's called AK uni, for uniform sampling of n-gram diversity.
Ah, clever. To capture rarer patterns.
Exactly. And they also specifically included names of foreign people and places, that's AKNEF for foreign named entities, and Indian names, AKNEI for Indian named entities. This variety lets researchers see how well the technology handles all these different kinds of words.
That sounds much more thorough than just looking at common words, which, if I remember correctly, was kind of a limitation of that older Dakshina test set you mentioned.
Precisely. Dakshina mainly focuses on those very frequently used words, often pulled from Wikipedia. The Aksharantar test set gives us a much broader and frankly more challenging way to see how good transliteration actually is across different situations.
Okay, let's go back to how they actually built this huge data set. You mentioned both automatic collection, the mining, and the manual creation. Can we dig a little deeper into those processes, maybe starting with how they automatically collected or mined the data?
Certainly. The automated process involves several pretty clever techniques. First, they gathered and combined existing collections of transliteration data. They pulled from sources like the Dakshina dataset itself, the IITB parallel corpus, and a few others. You can see in their research paper there's a table showing that even these existing resources were just much, much smaller compared to what Aksharantar ended up being.
Right, so they started with what was already out there. What else did they collect automatically?
They also collected a lot of data from Wikidata, focusing specifically on the labels for names of people and places.
Ah, because those often exist in multiple languages.
Exactly. The English label and the Indian language labels often naturally form transliteration pairs. For labels that had multiple words, they generated all the possible combinations and then used an automatic tool to filter out the pairings that seemed unlikely to be actual transliterations.
Smart. What about those collections of parallel translations, like Seminantar? How do you get transliterations from sentences that are supposed to be, well, translations?
Yeah, that's a more complex process. They first used tools, word alignment tools, to figure out which words in the translated sentences likely corresponded to each other. The tricky part, then, is to tell the difference between words that are actual translations and words that are transliterations. Think of proper nouns again, or maybe words borrowed from other languages that might appear quite similarly in both sentences.
Okay. How did they differentiate?
They used a statistical method. It basically tried to model these two possibilities. Is this paratransliteration or is it not? They used a repeated process, an iterative approach, to refine this and find potential transliteration pairs.
That sounds pretty sophisticated. Were there any pitfalls with that approach?
Absolutely. As the researchers themselves point out, this method could sometimes mistakenly pick up actual translation pairs, or sometimes words that have a lot of, say, suffixes or grammatical endings in one language but not the other. This could lead to incorrect transliteration pairs being identified.
Any examples?
Yeah, they give a couple, like a Hindi word for interconnected being wrongly paired with its English translation, or the word surname being linked to its Hindi equivalent. Even a place name that had a grammatical ending attached in the Hindi sentence could be misinterpreted by the system.
So how did they try to weed out those potential errors from getting into their data set?
They used a rule-based tool. We mentioned it briefly before. It basically checks the consistency of the consonant mappings within the potential word pair. This kind of check is often enough to catch those incorrect transliteration pairs that the statistical method might have wrongly flagged. We'll probably talk more about this tool later because they also used it during the manual data creation phase.
Got it. So existing data collections, Wikidata, parallel translations, What about those big collections of text in single languages, like Indicorp? How do you get transliterations when you only have text in, say, Hindi, without the English equivalent right there?
Right. That involves a clever kind of bootstrapping approach. What they did was first train some initial, maybe not perfect, but functional, multilingual transliteration models using the data they'd already collected from those other sources we just discussed.
Okay.
Then, if they had an Indian language word from Indicorp, they could use these initial models to guess a possible Roman script transliteration for it. The next step was to look for similar English words within the English part of Indicorp, based on how many sequences of 4 letters, character, 4 grams they had in common.
Okay, I think I see the logic there. Similar sounds might lead to similar letter patterns, even across scripts.
Hmm.
But how do they know if they found a real transliteration pair and not just a couple of words that happen to look a bit alike by chance?
That's where the scoring comes in. They scored each potential pair using their initial transliteration models, but crucially in both directions, from the Indian language to Roman, and then from that potential Roman word back to the Indian language.
Ah, a two-way check.
Exactly. Only pairs that scored above a certain threshold in this bidirectional scoring process were kept. They even mention the specific score they used in the paper, greater than Manigay's 0.35 log probability.
Interesting. And I remember you mentioning earlier there were some difficulties with less common languages during this automatic collection.
Yes, that's important. They found that some specific characters, particularly those unique to less common or lower resource languages, weren't really showing up in the automatically collected data at first. For example, a specific nasal sound character in Oriya, or a particular vowel sound in Punjabi.
Why was that?
Because the initial transliteration models, the ones trained on the data mined from Wikidata and Samantar, hadn't seen enough examples of these characters, so they simply couldn't automatically find pairs containing them when searching through Indicorp. To fix this, they actually did another round of this automatic mining after they had gathered some initial data manually for these languages. That manual data helped improve the models, which could then go back and find more examples containing these previously missing characters.
That makes sense. You need some initial seed data to get the process started for those less common languages. Now, you also mentioned they did a quality check on all this automatically collected data using human experts. What did they find? Was the mine data any good?
They randomly picked about 500 word pairs across 12 different language pairs from the mine data and had them evaluated by native language experts. And the results were actually quite impressive.
Oh, yeah.
They found that on average, 89% of the automatically collected pairs were valid transliterations. And even the lowest accuracy for any single language pair was still a respectable 80%. So this basically confirmed that the data they mined from sources like Samantar and Indicorp was generally very high quality.
That's reassuring. Were there any common types of mistakes they noticed in the 11% or so that weren't quite right?
Yes, they did identify a few recurring patterns in the invalid pairs. Mistakes involving vowels were the most common things, like adding or missing vowel marks incorrectly or confusing short and long vowels. They also saw errors with suffixes where maybe word endings were either transliterated incorrectly or just left out entirely, leading to sort of partial transliterations.
Okay.
And, perhaps not surprisingly, proper nouns were challenging because, a word in English can often be spelled and even pronounced quite differently when it gets adapted into an Indian language. However, they did note that even many of these technically incorrect pairs were actually partial transliterations, which could still be somewhat useful for training the AI models.
Okay, so the automated collection gave them a huge amount of data, and the human review confirmed it was mostly good quality. But as you said earlier, it wasn't enough on its own. It had gaps. Which brings us to the manual creation of transliteration pairs. Why was this so necessary?
Right. There were several key reasons, really. Firstly, as we discussed, the automatically collected data, the mine data, had a lot of proper nouns. Romanizations of more common, everyday words were actually less represented. They mainly came from the older Dakshina dataset, which itself focused heavily on just the most frequent words from Wikipedia.
So a lack of variety.
Exactly. A lack of variety, potentially missing many important transliteration patterns you see in normal language use. Secondly, the automatic process, particularly the mining from Indicorp, only worked really well for languages that already had enough digital resources available and relatively straightforward sound-to-script relationships. This left out some languages entirely.
Right.
And finally, they wanted to create a really high-quality, diverse, and accurate standard test set for evaluating transliteration across all the major Indian languages. And for that, you really need human curation.
So the manual creation was aimed at filling these gaps, getting more everyday words, covering more languages properly, and creating a much better benchmark for actually evaluating the technology. How did they go about this? Well, pretty massive task of manually collecting transliterations for 19 different languages.
It was indeed a significant effort, involving trained annotators from across India. The process started with carefully choosing the Indic words that needed to be converted into Roman script. They used IndicCorp as the source for 11 languages, another collection called the LDCIL corpus for 6 others, religious texts like the Mahabharata for Sanskrit, and Wikipedia for Manipuri.
Okay.
From these sources, they created unique lists of words for each language, and they filtered out any invalid words or words that appeared very, very infrequently. You can actually see in their paper there's a table showing how the size of these initial word lists varied quite a bit for each language.
And they didn't just pick words randomly from these lists for people to transliterate, did they? They had specific reasons, specific criteria for choosing certain words.
Absolutely. Their goal was all about ensuring variety and coverage. So they selected the top 5,000 most frequent words for each language, but they specifically made sure these weren't already in the existing Dakshina dataset. This was to add more common, everyday words to their collection beyond what Dakshina offered.
Makes sense. What else?
They also used a pretty clever method involving character language models. Basically, they trained these little models to assess how diverse the letter combinations or character engrams were within the words themselves.
Okay.
They then grouped all the words based on these diversity scores, from words with very common letter patterns to words with very rare ones. And they made sure they picked words evenly from each of these groups. The idea was to capture a really wide range of character combinations, not just the most frequent ones. They collected about 10,000 words per language using this enneagram diversity method.
That sounds like a really good way to get beyond just the most common stuff and capture more varied linguistic patterns. What about proper nouns, though? I thought the Mind data already had a lot of those.
It did, but the manual collection aimed specifically to create a high-quality test set of proper nouns across different categories. So they selected about 2,000 English proper nouns covering Indian names, foreign names, locations, organizations, and had those manually transliterated. This allowed them to specifically test how well the final models handle these different types of tricky named entities.
Okay, so they had their carefully selected source words for each language. How did they actually get them transliterated by people? What was the process for this manual creation?
They used a two-step process. You can think of it as like a maker-checker system. First, one person, the maker, would create multiple possible Roman script versions or transliterations for a given native Indic word. Then, a different person, the checker, would review the correctness of these suggestions. The checker could also add their own versions if they thought something was missing or better.
And how did they manage this? Some kind of software?
Yeah, they used a mobile application called Karya. They actually did some smaller pilot projects beforehand to sort of figure out common mistakes people made and to refine the instructions for the annotators. For example, they found that limiting the number of transliteration variants someone could enter for a single word helped to discourage people from just adding lots of unnecessary or frivolous suggestions.
So the people doing the transliteration weren't just working completely freeform. There were guidelines and maybe some tools to help.
Yes, exactly. They were specifically told to avoid unnecessary variations, like, say, just doubling vowels, unless it was actually linguistically important for that language. And crucially, they were also given access to that automatic rule-based validator tool we mentioned earlier.
Ah, the consonant mapping checker.
That's the one. It would automatically flag potentially incorrect transliterations. Now, the annotator, the maker, could choose to ignore these flags if they were confident their suggestion was correct, but it served as a helpful guide, especially for catching simple typos or inconsistencies. Then the checkers had the final say. They could accept, reject, or add variants. The final set of approved Roman script versions for that native word became part of the dataset.
You mentioned this automatic rule-based tool a couple of times now. Can you remind us how that worked again? It checks consonant mappings?
Yeah, basically, it was based on an existing method originally developed for English-Hindi transliteration. It essentially checks if the consonants in the potential romanization and the Indic word match up correctly according to expected patterns. To do this, it needs a list of vowels for both languages involved and, critically, a set of defined consonant mappings between the two. The researchers extended this idea to cover 14 languages, working with language experts to define these mappings and add any language-specific rules or exceptions. For instance, they have a table in their paper showing exactly how Canada consonants typically map to Roman letters.
And how does it perform the check?
It works by first stripping out the vowels and common non-content words from the English side. Then it tries to sequentially match each remaining English consonant block to its corresponding Indic language consonant based on those predefined mapping tables. Finally, it compares the Indic forms generated this way with the original Indic word to decide if the romanization seems valid according to the rules.
And was it accurate? Did it help without being too strict?
They actually tested how well it worked on the Dakshina dataset first. They found it had a minimum accuracy of 90% for most languages, which showed it was a pretty useful tool and wasn't likely to reject too many correct transliterations. It was a good balance.
And this whole process of managing the people doing the work, giving out the tasks, ensuring quality, how was all that handled for such a large-scale effort?
They used Project Karya for that. It's an open source platform that Microsoft Research developed specifically for managing this kind of distributed data collection and annotation work. The platform allowed them to manage the whole workflow, distributing the word lists, collecting the transliterations, assigning checker tasks, and managing the workers, who were all working remotely.
I see.
Each task in the Karya app typically contained about 100 native words that needed to be transliterated by the maker and then subsequently checked by the checker. They specifically chose people for the main large-scale task who had already performed well in the initial smaller pilot projects, making sure their error rate stayed below 5%. And, importantly, the workers were paid for each word they processed.
Right. So after all that huge effort, the automatic mining and the careful manual creation, they had this massive Aksharantar data set. How did they then organize it to actually train and test their transliteration technology?
They combined both the automatically collected data and the manually created data. Then they divided this combined data set into standard sets for training the AI model, for fine-tuning its internal settings, often called a validation or development set, and for the final testing.
And the test set?
The test set, as we discussed before, was made purely from the manually created data, and it divided into those specific subcategories we mentioned earlier: AK-freq, the frequent words; AK-uni, words chosen for letter combination diversity; AK-nef, foreign proper nouns; and AK-nei, Indian proper nouns. And importantly, they took really strict steps to make sure there was absolutely no overlap between the data used for training the model and any of the data used for testing or validation, including that older Dakshina test set. This is crucial to get a truly unbiased measure of how well the technology actually performs on unseen words.
Makes perfect sense. You need a clean test. And all this incredible work on building the dataset then led directly to the creation of a powerful new transliteration model, right? That's where IndicXlit comes into the picture.
Exactly. Using this comprehensive Aksharantar dataset, they trained IndicXlit. Now, IndicXlit is a single AI model that can handle transliteration between Roman script and all 21 of the Indic languages included in their dataset, all in one model.
Ah, so not separate models for each language. Why go for one big model?
That's a good question. They chose to train one single multilingual model for several reasons. Firstly, it allows the less common languages, the ones with less data, to effectively learn from the pattern seen in the more common high-resource languages like Hindi. This is called cross-lingual transfer.
Okay, borrowing strength.
Exactly. Secondly, previous research has suggested that this kind of joint multilingual training can actually lead to better, more consistent sort of canonical spellings in the output. And thirdly, from a practical standpoint, it's just simpler to deploy and maintain one single model rather than dozens of separate ones.
Right, makes sense for development and use.
Hmm.
So how does IndicXlit actually work? What's its underlying structure, technologically speaking?
It's based on what's called the transformer architecture. This has become incredibly successful in, well, pretty much all areas of language-related AI tasks over the last few years.
The standard these days, almost.
Pretty much.
Yeah.
You can think of it as a very sophisticated way for the AI to pay attention to different parts of the input in this case, the sequence of Roman letters simultaneously when it's trying to predict the output, the sequence of native script characters. It's a powerful method. Specifically, IndicXlit is an encoder-decoder model. It works at the level of individual characters.
So letter by letter.
Essentially, yes. It takes a sequence of Roman letters as input, along with a special tag that tells it which Indic language it should convert to. And then the decoder part generates the corresponding sequence of characters in that target native script.
Hmm.
The input vocabulary is just the 28 Roman letters and symbols they used, and the output vocabulary is all the unique characters combined from all 12 Indic scripts in the training data, which adds up to about 780 different Indic characters.
Wow, 780 output possibilities. Sounds complex. What about the training process itself? Any interesting details there? How do you teach such a model?
They used a specific software toolkit called FAIRSEC, which is popular for this kind of sequence-to-sequence modeling. The model itself has several layers, 6 layers in the encoder and 6 in the decoder that process the input and generate the output. They used a particular type of activation function called GELU and applied standard techniques like dropout and layer normalization to prevent the model from just memorizing the training data, which is called overfitting.
Standard good practices.
Right. They used an optimization algorithm called ATOM to adjust the model's internal parameters based on the data, with a carefully chosen learning rate schedule to control how quickly it learns. And interestingly, to deal with the fact that they had much more data for some languages, like Hindi, than others, they used a technique called temperature sampling during training. This essentially gives more weight or importance to the data from the less common, low-resource languages, ensuring they don't get drowned out.
Ah, balancing the scales a bit.
Exactly. They also spent time fine-tuning the model's hyperparameters, things like dropout rate, learning rate on that separate validation set we talked about. The whole training process ran on powerful GPU servers for a significant amount of time, about 5 days on 16 GPUs.
Okay. And once the model is trained and you give it a Roman word, it might come up with a few potential transliterations, right? How does it decide which one is the best or most likely correct one?
That's right. During inference, when you actually use the model, they employ a technique called beam search. This allows the model to explore multiple possible output sequences simultaneously and keep track of the top few most likely ones. In this case, they kept the top 4 candidates.
Okay, so it generates 4 options. Then what?
Then, they re-rank these top 4 candidates using a revised scoring method. This new score is a combination. It takes the model's original confidence score for that transliteration sequence, how likely it thought it was based on the characters, and blends it with a score from a separate language model. This second model works at the word level. It's a simple unigram language model trained on Indic word frequencies.
Why add that second score?
The idea is that this word-level language model helps to favor candidates that are more likely to be actual real words in the target language. So if the main model produces a sequence of characters that's very probable according to its own rules, but doesn't actually form a common word, the language model score will be low, potentially pushing a slightly less probable but more word-like candidate higher up the ranking. They found through experiments that giving a weight of 0.9 to the original transliteration model score and zero point 0.1 to the language model score worked best.
Okay, that makes a lot of sense, using both the fine-grained character-by-character probabilities and the broader context of what real words generally look like in the language. Smart. So the big question, how well does IndicXlit actually perform? Let's talk about some results. Did it beat the previous best?
The results are actually quite impressive, yes.
Mm-hmm.
When they compared IndicXlit to the best results previously reported on that older Datasets test set, they saw a really significant improvement. We're talking about a 15% average increase in accuracy across the 12 languages covered by that specific test set.
15% average jump. That's huge in this field.
It really is. It clearly shows how much benefit came from using the much larger Aksharantar training data set and also from that multilingual training approach, learning from multiple languages at once. They even noted the biggest improvements were seen in languages like Marathi and Gujarati, which are closely related to Hindi, a high-resource language, suggesting that cross-lingual transfer was really effective. It's like having a much smarter autocorrect specifically for Indian language transliteration.
That's a great way to put it. What about on their own test set, the Aksharantar test set? How did it fare across those different types of words, the frequent ones, the diverse ones, the names?
Right, looking at the Aksharantar test set, they noticed some interesting patterns. As you might expect, the model performed best on the AK-Frick set, the one containing common frequent words. The accuracy there was pretty similar to what they saw on the Dakshinid dataset. This suggests that, generally speaking, frequently used words are easier to transliterate correctly.
Okay, that makes sense.
However, the AK-Uni set, the one designed with more varied and sometimes rarer letter combinations, proved to be significantly more difficult. The average accuracy on AK-Uni was about 10 percentage points lower than on AK-Freak.
Ah, so capturing those less common but diverse linguistic patterns is definitely harder.
It seems so, yes. It requires the model to have learned more subtle or less frequent mappings.
And what about those proper nouns? We know they were a significant part of the training data, both mined and manually collected for testing. How did it handle names?
Well, somewhat surprisingly, the proper noun test sets both the foreign ones, AKNEF, and the Indian ones, AKNEI, turned out to be the most challenging for the model. Foreign proper nouns were particularly difficult.
Why do you think that is?
It's likely because there's often a much greater difference between how a foreign name is spelled in English and how it's actually pronounced, and therefore needs to be written in various Indian languages. There's more ambiguity, more potential variations.
Right, and Indian names.
Indian proper nouns perform better than the foreign ones, but their accuracy was still generally lower than even the uniformly sampled words, AK-uni. The researchers found this a bit unexpected and mentioned it's something they want to investigate further. They also noted, consistent with other findings, that languages using the Arabic script, like Urdu and Kashmiri, or those languages that simply had less training data overall, the lower resource languages, tended to have lower accuracy across all the test sets.
Okay. You mentioned earlier that using that word-level language model to re-rank the top 4 candidates helped improve things. By how much did it boost the accuracy?
On average, this re-ranking step improved the final transliteration accuracy by a very significant 12% across all languages when looking at the top 1 prediction. That's a substantial gain just from adding that simple word-level check.
12%, wow.
However, it's worth noting that this benefit was mainly seen for the native language words, like those in AK Frick and AK Uni, and particularly for the more common higher resource languages, where they had enough data to train decent word-level language models.
Ah, so it didn't help as much everywhere.
Right. For the proper nouns, both Indian and foreign, and for the lower resource languages, the re-ranking didn't provide nearly as much of a boost. This is likely because those rarer words, or words in languages with less data, might not be well represented in the simple unigram language models they use for re-ranking. The language model just doesn't know those words well enough to help.
Got it. And to really understand where the model was still having trouble, even with the re-ranking, they also did a detailed analysis of the errors it was making, right? What are the main types of mistakes IndicXlit was still prone to?
Yes, they manually looked at the model's output for several languages to categorize the errors. The most common type of error across the board was related to vowels, things like adding or removing vowel diacritics, measures incorrectly, or mixing up short vowels and long vowels. That seemed to be a persistent challenge.
Okay, vowels are tricky. What else?
They also saw cases where the model confused similar-sounding consonants. Other notable error types involve gemination. That's the doubling of consonants, which can be inconsistent in romanization. Acronyms were another tricky area, as they often have their own unique transliteration styles that don't follow normal rules. And sometimes, there were situations where the correct transliteration was ambiguous just from the letters alone. You might need more context.
Contextual ambiguity, right?
Exactly. They also noted some error types that seemed to be more specific to certain languages or scripts. And interestingly, they also found that in quite a few cases, what the model produced wasn't technically the single correct answer in their test data, but it was actually a valid alternative way to transliterate the word. Transliteration isn't always one-to-one.
That's a really important point. It's fascinating to see the subtle complexities involved, even in something that might seem straightforward on the surface. Now, I know the researchers also did some extra experiments, ablation studies, to understand how different parts of their approach contributed to the overall success. What were some of the key findings from those?
Yeah, those experiments provided some really valuable insights. They confirmed that adding transliteration pairs from various sources consistently improved accuracy. And specifically, the data they mined from the large Indicorp collection of monolingual text seemed to have a particularly big positive impact.
So IndieCorp was really important. What about the manual data?
Interestingly, adding the manually created data didn't dramatically improve performance on the Dakshina test set. This is probably because Indicorp mining already provided good coverage of the common words that dominate Dakshina. However, the manual data did show clear improvements on their own more diverse Aksharantar test sets, especially AK-Uni and the named entity sets. This highlights its importance for capturing that wider variety of words and also for boosting performance in the lower resource languages where mined data was scarce.
Okay, so manual data matters for diversity and low resource. What else?
They also explicitly confirm the benefits of training a single model on multiple languages, the multilingual approach. Especially for those lower resource languages, the multilingual model performs significantly better compared to training separate models just for each language individually.
That confirms the cross-lingual transfer idea.
Exactly. They also found that models designed to handle characters from different but related scripts, like all the Brahmi-derived scripts together, performed pretty much just as well as models trained only on a single script. Given the practicality benefits, this supported their choice of using multi-script models. And while models trained specifically on just one language family, like only Dravidian languages, showed a slight edge in some cases, they ultimately chose to build a single pan-Indic model covering all families for maximum ease of use and deployment.
Makes sense. And the re-ranking.
And yes, as we've already discussed, their experiments clearly showed that using that simple word-level unigram language model to re-rank the top candidates gave a very significant boost in the final accuracy. It was a simple but effective addition.
It sounds like a very thorough and insightful research effort all around. In their conclusion, what did the researchers really highlight as the main takeaways, and what are some of the limitations or future directions they're thinking about?
Well, they strongly emphasized the significance of Aksharantar itself as this large-scale, diverse, and crucially publicly available resource. They see it as marking a major step forward for enabling better Indian language transliteration research and development, and they reiterated the significant improvements in accuracy achieved by their IndicXlit model, showcasing the power of large data sets and multilingual training.
And limitations.
They did acknowledge some current limitations. For instance, their benchmarking primarily focuses on relatively clean, well-formed words. Real-world online text, as we know, can be much messier with typos, code mixing, non-standard spellings. That's a harder challenge. They also mentioned their ongoing work to expand their benchmark datasets to cover even more languages. In fact, they noted that Dogri was released subsequent to the paper.
Ah, so it's growing.
Yes. And while this particular work focused heavily on evaluating transliteration at the individual word level, they have since released datasets for evaluating performance at the sentence level as well, which is important for real applications. And finally, although their initial big push and the model described here focused on converting from Roman script to native Indic scripts, which is arguably the more common need for input methods, they have also now released models that can do the reverse, convert native scripts back to Roman script.
Good to have both directions.
Definitely. Ultimately, their hope is that the Aksharantar dataset and the IndicXlit model will serve as a strong foundation and really encourage further innovation in Indian language processing and all its various applications, from keyboards to search engines to content moderation.
Okay, so just to recap the core message here, Aksharantar is this huge, carefully constructed, and diverse collection of data specifically for Indian language transliteration. It was built using a smart combination of automatic mining techniques and painstaking manual annotation. And this data set has enabled the development of IndicXlit, a powerful single AI model that significantly improves how accurately we can convert Roman script input into the correct native Indian language scripts, covering a wide range of languages.
Exactly. This research has really created an invaluable public resource and a very strong technical foundation for future progress in this critical area.
And what does this all mean for you, the listener, tuning in?
Well, fundamentally, this research directly helps make digital communication more accessible, more seamless, and just generally more user-friendly for potentially over 1 billion people. By making transliteration tools more accurate and more widely available, it helps bridge that gap between the convenience of typing on standard Roman keyboards and the richness, the expressiveness of native Indian language scripts. It makes technology feel more inclusive, more natural for vast multilingual communities. Think about just trying to search for a specific restaurant name online or a person's name. If the transliteration the search engine uses isn't accurate, it can be incredibly frustrating, right? You just can't find what you're looking for. Absolutely. We've all been there.
This research is directly addressing those kinds of real-world, everyday problems.
And what's really fascinating to think about, perhaps, is the future this kind of work opens up. Can you imagine even smoother, more intuitive ways of interacting with technology using Indian languages online? Resources like Aksharantar are basically the fuel for that potential. So maybe a final thought for you to consider. How might advancements like these change your own experiences with Indian languages online, if you use them? Or perhaps just deepen your understanding of what the digital landscape looks like and the challenges involved for incredibly diverse populations around the world. It's definitely something worth mulling over. And remember, if you're technically inclined or just curious to poke around, the Aksharantar datasets and the IndicXlit models are publicly available for you to explore.